Right. Hello, everyone. My name is Zach Hicks. I work as a communications engineer at the Johns Hopkins University Applied Physics Lab. I'll be presenting Pluto Pink, enabling FPGA accelerators in low-cost SDRs. That's specifically the Pluto SDR and derivative platforms. This research was completed as a part of my master's thesis at the Johns Hopkins University Engineering for Professionals program. So I'd just like to thank the EP program for sponsoring my presentation at GRCon this year. Here's a quick agenda. I'll talk through some of the motivation here, a quick background on what Pink is, if anybody's unfamiliar, talk about the details of building a Pink Linux image for SDR. I'll show a DSP overlay example for the ANT SDR, and then wrap up with some conclusions. So bottom line up front here, Pink is an embedded Linux image that provides a Python environment for designing, loading, and using FPGA accelerators on Xilinx Zynq SoCs. So what I accomplished in this research, I was able to boot a Pink image for the Pluto SDR using an external USB root file system. This included the integration of the Analog Devices Yocto layer to include those RF transceiver kernel drivers. Unfortunately, during the course of my research, I encountered an unrecoverable kernel boot failure after attempting to integrate a kernel patch for those ADI drivers. So I pivoted under the time constraint of my thesis research to use the ANT SDR E200 to implement a demonstration hardware-accelerated FM radio receiver. So the motivation for this research was really how to isolate the FPGA in software-defined radio for beginners. So as everybody here knows, SDRs are very complex and multidisciplinary devices, but learning DSP hardware should not require the implementation of a full embedded Linux system. So my research question was, how to isolate the FPGA to make implementing signal processing as simple and low cost as possible. Quick overview of Pink. So Pink is an open source Python framework for Zynq SoCs. The block diagram on the slide here kind of shows the different layers that make up Pink. At the very bottom layer, you have FPGA accelerators that are bit streams. They're called overlays. Pink provides some Linux kernel drivers and a Python API for controlling your bit stream from an interactive Jupyter notebook that runs on the embedded system, and you can connect from your host computer. Pink is made up of two primary components. There's the PetaLinux kernel. PetaLinux is the Xilinx tool for creating Linux images for their SoCs. And then Pink uses a full Ubuntu root file system. The fundamental trade-off of Pink is a simplified path to hardware-software co-design at the cost of efficiency. So because this is a Python interface and it's kind of all done for you, this is not a very high-performance system, but it is very easy to integrate. Xilinx sells an RF system-on-chip development kit to academic customers called the RFSoC Pink. There is first-party support for a Pink image that includes a Python API for the RF data converters and some demonstration Jupyter notebooks that show DSP overlays and visualizations of transmit and receive chains. However, this kit costs over $2,000, which is not really accessible for students or hobbyists. So I was trying to emulate some of this capability at a much lower cost. So the right SDR platform has to be affordable for students and hobbyists. It has to have FPGA DSP resources and has to be compatible with Pink. So the radios that kind of meet all these requirements are the Pluto SDR and derivative platforms. Some issues with the Pluto SDR when it comes to Pink. There's not enough flash memory to store that full Pink image. So the Pluto only has 32 megabytes of onboard flash memory. And like I mentioned before, Pink uses a full 8 gigabyte Ubuntu root file system. There's also no existing Pink support for any Analog Devices IP, specifically their fork of the Linux kernel that includes all the RF transceiver drivers. The ANT SDR is a Pluto SDR derivative platform. It's basically the same hardware plus an SD card slot and gigabit Ethernet. The SD card slot kind of solves that flash memory limitation, but some issues with the E200 are it has a long lead time, and there's less support and documentation in the Pluto SDR. That's kind of one of the great benefits that the Pluto provides. Here's a photo of the Pluto Pink hardware setup. It's kind of Frankenstein together. You can see the Pluto SDR on the far left, connected through a USB on-the-go adapter to a USB hub. The external USB storage is used to store the Linux image and the root file system. And then the USB JTAG bridge is used to interact with the U-boot console to actually boot the Pink image. The total cost of all these components comes out to $320. Here's a photo of the ANT SDR E200 hardware setup. You can see it's a much simpler setup, primarily because of the addition of the SD card slot. The total cost here comes out to $329, only $9 more than the Pluto plus all the added accessories. Here's a quick flow chart of the Linux boot process on the Zynq 7000 SoC. The two pieces that are really relevant for Pink are the second stage bootloader and the kernel. So in the Analog Devices Pluto SDR firmware, they already support booting FIT images. This is a Linux kernel image format that kind of combines all of those three components into one binary file. And they also already enable the USB subsystem. So in order to boot your own Linux image on the Pluto SDR, all you have to do is load it onto a USB storage drive and then load that image into RAM from the U-boot console, and then you can just boot into Linux from there. So the Pluto Pink system actually did not require any modification of the Pluto SDR firmware in the flash memory. You can see on the slide there just some outputs showing the USB storage detected. The Pink system uses the Petalinux tool, which is, like I said, the Xilinx tool for creating Linux images on their SoCs. Petalinux allows you to configure kernel features through a menu config, and then all that configuration can be exported as a board support package. Petalinux is built on top of Yocto, which is an open source collection of recipes and tools for creating embedded Linux images. This contrasts with Buildroot, which is kind of the other tool for creating embedded Linux images. That's what ADI used to build the Pluto SDR firmware. So basically, I just had to take all of the Buildroot kernel config and map that into Petalinux and Yocto. Once that was done, I had to add the Analog Devices Meta ADI Yocto layer that allows the integration of their fork of the Linux kernel and all of the device drivers required to control the RF transceiver. As you can see, a couple screenshots from the Petalinux menu config on the slide that show the integration and enabling of the 809361 kernel driver. On the user space side of the Pluto Pink image, all of the IAO software is required to actually enable control of the transceiver from software. So you can see all of these software packages were included in that Ubuntu root file system that allows software running on the Pluto SDR to control the RF transceiver. And also IAOD was included to allow control from remote contexts. So this enables the Pluto Pink system to kind of become transparent to a host computer. So when the system boots up, you can still stream samples into GNU Radio on a host computer totally transparently. The system doesn't know that it's running Pink. Microphase is the manufacturer of the ANT SDR E200. They provide a Pink image for their radio. However, they include the ADI kernel drivers using a 900,000 line kernel patch, not the Meta ADI Yocto layer. And then they build their device tree overlays using the Pink PRIO project from a research group at BYU. Their Microphase Pink image did not include any of the user space transceiver control software. They required on-platform installation of all the IAO and Python bindings software. So I created a repository fork of their repo to add in all of the missing IAO packages and automate their build process. Like I mentioned earlier, I encountered a boot failure on my Pluto SDR during the course of this research. So I attempted to integrate the ANT SDR kernel patch into my Pluto SDR image. The Pluto failed to boot using this kernel patch, and strangely, all future boot attempts also failed. This included using Linux images that did previously work, and this failure persisted across a full restore of the U-boot firmware. So I'm not really sure what went wrong there. Under the time constraint of my thesis, I had to pivot, so I used the ANT SDR Pink image that I modified to ensure that I could create a demonstration overlay. ADI provides a great HDL reference design for like the Pluto SDR, FMCOMS2, kind of all those derivative platforms. You can see the data path shown on the slide there. So I broke the received data path between the AXI interface that actually controls the RF transceiver and the receive FIFO. I inserted an empty overlay block diagram in the Vivado project to serve as a wrapper for user signal processing logic. Within this overlay template, basically I provide the user with only the signals that they need to implement signal processing IP. So there's a sample clock that's generated from the transceiver and buffered into the Zynq FPGA fabric as L clock. The frequency is derived from the requested sample rate on the transceiver. All the signal processing is done on L clock to avoid crossing clock domains, so keeping it simple. And then there's an asynchronous reset provided from a pink GPIO signal from the PS on the Zynq. So basically all the user needs is the data signals, the valid signal, clock, and reset. Along with my overlay template, I provide a test bench. So this allows you to instantiate an HDL wrapper for your pink overlay, just for verification of whatever signal processing IP you've implemented. So this allows you to load your own IQ file, set your sample clock rate, etc. So FM radio receivers are kind of the hello world for wireless communications, so that's what I chose as my demonstrator overlay. So you can see this is just a stock GNU Radio, all software FM receiver flow graph. And what I did was I took the rational resampler that performs an initial decimation by 5 and pushed that into the FPGA. So here's the Vivado block diagram for those decimation FIR filters. I implemented this somewhat trivially using the Xilinx FIR compiler IP, and then I generated the impulse response using Python. So this produces kind of a heterogeneous DSP system where the FPGA overlay provides the initial decimation by 5. That reduces the sample rate required to be transferred over that Ethernet or USB interface. You then stream the samples to the host computer at a lower sample rate, and you can perform the FMD mod in software. So here's a demo video of how this works. So you can see in the lower left, there's the Linux kernel boot logs from the Ant SDR. Once we get into user space, you'll see the device tree overlay nodes that are added when the base image is loaded. So then in GNU Radio, you can just run a FM radio receiver flow graph like Pink is in there. So then I'll go to the Jupyter Notebook interface, and I'll open up the decimation FIR filter Jupyter Notebook. Here in this notebook, you can see the Python code used to load the overlay. So first import the Pink Python packages that are required, and then load the overlay bit stream from the Jupyter Notebook. And then I will assert and deassert the asynchronous reset signal. You can see in the lower left, the device tree nodes being reinserted. And then back in GNU Radio, you can see the same FM receiver flow graph. Running down a hill can lead to that pain. Demodulating an FM radio station, but the initial decimation by 5 is now being performed in the FPGA, totally transparently. So some takeaways in future work here. Pink might not be the best choice for some of these resource-constrained platforms. So although this did work, what I was hoping to be able to do was stream samples through the IIO interface on the platform, do some initial software processing on the Zynq CPU, and then transfer them via ZMQ to a host computer. That turned out to run pretty slowly. I think there's opportunity to improve that using like the C++ bindings that are being developed for Pink, or maybe just a lighter weight framework that doesn't use Pink. Some future work, obviously repairing the Pluto SDR Pink image would be the first thing that I'd like to do. And I think it would be also nice to pursue some tighter integration into GNU Radio. Right now, all of the signal processing that's happening inside the FPGA is not really obvious from the GNU Radio flow graph. So I think it'd be great to allow overlay loading directly from the flow graph and provide some indication that processing is being done on the samples before they arrive into GNU Radio. That's all I have, so take any questions.
Yeah, good work. How long did it take you?
I started this work in January of this year, so it was January to August.